Okay, so what is this video about? This video is doing tutorial 2 again, same as the last two videos, except now I am going to use the tables. Okay, so before we in the previous videos, I was using the isentropic flow functions. Okay, so basically I'm using these sets of formulas to solve problems. This time I'm going to use tables. Okay, so when I say tables, I mean this table. Okay, the flow function tables. Okay, so let's get started. So question one, take a look. Okay, air is extracted through a nozzle from a large tank in which temperature. Okay, so let's draw out the problem. Okay, so we have a large tank. Then here's the stagnation point, right? They say the velocity of air in the tank is negligible, and hence we can consider those conditions as stagnation conditions. Okay, so there's a flow, an isentropic flow, which leads to a point we call point one. Okay, so inside the tank, the temperature is 70 degrees Celsius. Convert this to Kelvin is 343 kelvins. Stagnation pressure is this 101 kPa. And here at point one, we have a pressure of 25 kilopascals, a diameter of 0.15 meters. Then the area can be calculated using pi d squared over 4. Okay, so find m dot, right? We're expected to find the mass flow rate. So the mass flow rate is found by, okay, rho AV. I'm going to use the properties at point one. So rho one, A1, V1. We have A1. We do not have rho one or V1. Okay. So what are we supposed to do? Okay. First, we need to know the Mach number at point one, right? We do not know what's the Mach number at point one. And Mach number is usually what you need to find first in any type of compressible flow problems, whether it's isentropic, whether it's normal shock, Rayleigh flow, or fan of line flow. You're always going to find the Mach number at a point first. Okay, so how do you find the Mach number? Well, take a look at the given conditions here and the given conditions here. Where do you see both static and stagnation conditions exist? So what I mean is, for example, here, uh, the stagnation pressure exists along with the corresponding static pressure. See, we have the two versions of the pressure, the static and the stagnation one. So when you have both of these properties at the same time, you are able to find the Mach number. Okay. In the last few videos, I used the flow functions. So this time I'm going to use the tables. So how would we deal with the tables? Well, let's take a look at the tables. Okay, so in this table, look at the column heading. Okay, specifically we want to look at the pressure, right? Yeah, so let's take a look at pressure. In pressure, we see this ratio. Let me write it down here. Okay, we see this ratio P over P naught, right? All of these ratios, the temperature ratio, the pressure ratio, the density ratio, and the area ratio, all these are a function of Mach number. Okay, what do I mean by it is a function of Mach number? That means as Mach number changes, the ratio, whether it's the temperature ratio, the pressure ratio, the density ratio, or so on, it will also change. So let me say that again. The condition ratios, okay, these ratios are a function of Mach number. Okay, so for example, T over T naught is a function of the Mach number. And this means as the Mach number changes, let's say for example the temperature ratio also changes. Okay, likewise for the pressure ratio, as Mach number changes, the pressure ratio also changes. Okay, so that's what you have to keep in mind. That's why Mach number is so important, because once you have the Mach number, you can find the, let's say, the pressure ratio accordingly, or you can find the temperature ratio accordingly. Okay, that's why Mach number is so important in the compressible flow problems. Okay, so how do we write out this in our working? Okay, so we wanted to care about the pressure ratio, right? So here we have P over P naught. But we want to apply this to point 1, right? So instead of P over P naught, we write P1 over P naught, okay? This shows that we apply it to point 1. So let's go back to here. Okay, so we write P1 over P naught is a function of Mach number, okay? So this is how we denote it. So what else do I need to write? I need to write here a subscript, which says Eisen, okay? Eisen means isentropic, okay? Then what else? Because we are applying this to point 1, right? The Mach number here must be M1, okay? So this must be M1, okay? If this is P1, this must be M1, okay? If this is P2, then this must be M2, okay? So why do I need to write Eisen down here? Because, right, there are different types of flow function tables, okay? The one I showed you here, see, look at the title. It says isentropic flow functions. Let me show you a different table. How about this one? This one says normal shocks. So different tables, right, have different functions. That's why you need to specify, okay? You need to specify down here isentropic. If we're dealing with normal shocks, then we will have to label it as normal shocks. Okay? So that's why this tells me that I'm getting this from the isentropic flow table. Okay, the isentropic flow table. Okay, so that is what this F tells me, is that I'm getting this from the isentropic flow table. Okay, so now we can substitute the known values. Okay, we're given P1 and P0, right? They're given here. So let's substitute them in. So 25 kPa divided by 101 kPa, and then okay, M1 is unknown. We want to find M1. So if you calculate this out, right? If you calculate 25 over 101, you will get 0.2475. Okay, so what does this mean? What does this mean here? This means that I need to go to the isentropic flow table and find the row in which the pressure ratio is equal to 0.2475. Okay, let me say that again. I need to go to the isentropic flow table, find the row where this pressure ratio has a value of 0.2475. Okay, so let's go take a look at the isentropic flow table. Okay, so here is the pressure column, right? So we only focus on this column. And then now we need to find when the entry in this column is equal to 0.2475. So let's go ahead and find that value. Okay, so now let's look at this one. Okay, still not here. Okay, so it's gonna exist somewhere in this column, right? You see, over here, we're close to the range of values, right? We're looking for, remember, 0.2475. But the thing is, this exact value, 0.2475, does not show up in any of the entries of this column. Okay, so what we need to do? What we need to do is just to do an estimate, meaning we just take the entry which is closest to 0.2475. So which of these entries here in this column is close to 0.2475? And I'm just gonna say that it is close to this one. Okay, 0.2496 is the closest entry we get to 0.2475. So how do we find the Mach number at point 1, having identified this entry? So what we need to do is we go take a look at here, right? Because the leftmost column shows Mach number, right? And then, yeah, so the corresponding Mach number to 0.2496 is 1.56. Okay, so that is how we solve for the Mach number here, because this one is unknown, right? So we have found that M1 is equal to 1.56. Okay, let me be specific. This is just an estimate. Okay? An estimate. So how do we get this? We got this from the tables. Okay, from the table. Okay, so I hope that's clear to you. So let me say again. Okay, we want to find the Mach number at point 1. So what we need to do, we need to use a stagnation pressure and the static pressure. Okay, So we know that the pressure ratio is a function of Mach number, so we write like that, okay? And it must be specified to the isentropic flow table. Okay, so we substitute those pressure in, calculate that is 0.2475. So what we need to do is go back to the table. Okay, go back to the table, look at the pressure column, which is this column here, and then find the entry which is closest to 0.2475. Here in our case, we found it to be 0.2496. This is already the closest we can get. From there, you look at the corresponding Mach number, and the corresponding Mach number we found is 1.56. Therefore, we conclude that the Mach number at point 1 is about 1.56. Okay, this is just the estimate only because there's a lot of rounding off. So yeah, this is how you estimate the Mach number using the tables. Okay, so having found the Mach number, what we can do is next we need to find the temperature. Okay, the reason why I need to find temperature is because of this. So we want to find V1, right? Remember the Mach number definition is M is equal to V over C, right? We can rearrange this to make V the subject. Okay, so we already found M1, but we do not know what is C1, right? C1 is given by KRT1, but we do not know what is temperature, so therefore we need to find temperature at point 1. Okay, so again, you go back to the tables, right? Hold on. Okay, you go back to the tables. The tables show that we have this temperature ratio column. So T over T naught. Because we want to find it at point 1, we label it as T1. Okay, so T1 over T naught. So go back here. Then, okay, so T1 over T naught. Okay, again, it is a function of your Mach number at point 1. But here, now, Mach number is already known, right? So let's label here. Mach number is equal to 1.56. Okay, so now let's substitute what we know. We know the stagnation temperature. And then we can get this value from the tables. Okay, so let's go to the isentropic table and go to the row where it says Mach number is 1.56. Okay, go back here. Okay, go back down to the row where it says Mach number is equal to 1.56. Yeah, so basically it's just the row that we uncovered just now. So this one, right? And then the temperature column is the first one here. Okay, see, the temperature column is this one here. Okay, so we go down and take a look. Oh, sorry. Yeah, we can see that the temperature ratio at Mach number 1.56 is equal to 0.6726. Okay, so let's go back and replace this with 0.6726. Okay, how do I get this? I got this from the table. Okay, just as a reminder. Okay, so now if you make T1 the subject, you will find that the temperature at point 1 is about 230.7 Kelvin. Okay, so now we can find V, which is M1C1. M is 1.56. C1 is given by square root of K R T. Okay, then velocity, if you calculate it, it should be 474.958. Okay. What else do we need to find? Okay, so we already found velocity. Now we need to find the density. Okay, so how do you find density? Density is found using the equation of state, otherwise known as the ideal gas law. P1 is equal to rho R T. Okay, so we can rearrange this to make rho the subject and then substitute the known values. So P is given here. T is what we found just now. Here. Yeah, so we can find density. Okay, so change kilopascals to pascals. We have this 25,000. And temperature is 230.7. Punch this in your calculator and you should get 0.378. Finally, we are in a position to calculate mass flow rate. So density, cross-section area, times velocity. So velocity is given by 474.9. Okay, you should be able to calculate 3.17 kilograms per second. Okay, and this is slightly off from the version where we use the flow function. The flow function was 3.18, but in here it's 3.17. It's good enough for you. Okay, so now let's move on to question 2. Question 2 states, okay, so at a section in the channel, an air flows with the condition as this. Yeah, okay, so let's sketch out the problem. So this is point 1, this is point 2. Point 1 has these conditions. Remember to change degrees Celsius to Kelvin. Okay, then okay, so what are we expected to find? Determine the Mach number. Okay, yeah, so we expected to find M2. Okay, so find M2. Okay, this is isentropic flow. Okay, so what is special about isentropic flow? As I mentioned before, the special thing about isentropic flow is that any 2 points on the isentropic flow share the same stagnation conditions. This is a critical fact of isentropic flow. So let me write that down. The special fact about isentropic flow is that any 2 points on isentropic flow share the same stagnation conditions. And what do I mean by stagnation conditions? Okay, what I mean is, okay, the T naught, P naught, rho naught, yeah, these are the main stagnation conditions. Okay, so they share the same stagnation conditions. Therefore, since you know that 1 and 2 fall on the same isentropic flow, they share the same stagnation conditions. Okay, so that means T naught is the same, P naught is the same, rho naught is the same. Okay, with that in mind, we should find the stagnation conditions first. Okay, but in order to find the stagnation conditions, we need to know the Mach number at point 1. Okay, so let's go ahead and find the Mach number. So Mach number is given by V1 over C1. Is V1 given? Yes. Okay, this is given. This is found using square root of K R T1. So therefore, we can calculate it. So 120 divided by square root of K R T1. Okay, you will find that the Mach number is about 0.3558. But I'm going to round it off even further to just 2 decimal place, and you'll see why. Okay, so okay, now what do we want? Okay, so having found the Mach number, right, we are in a position to find the stagnation pressure, right? The stagnation pressure. Okay, so let's go ahead and find the stagnation pressure. Why pressure specifically? Because they give me pressure here. So that means I need to use I need to find the stagnation pressure. Okay, so how do you find the stagnation pressure? Remember in the table, right? We have a column which says P over P naught, right? So applying this to point 1, it will be P1 is equal to okay, this pressure ratio is a function of, so let me write this down properly. This is a function of the Mach number at point 1. And then we found that the Mach number at point 1 is this. Okay, 0.36. So let's go ahead and substitute whatever we know. Pressure at point 1 is 150 kPa. And then what is this? We obtain this from the table. Okay, so you go to the table and then look for the row where the Mach number is equal to 0.36. Okay, so let's take a look. Where is Mach number equal to 0.36? Over here. Okay, and specifically we are looking for pressure ratio, right? Okay, so pressure ratio is in this column. Okay, So let's go down this column and it'll be here. So the pressure ratio will have a value of 0.9143. So let's go back here and then replace that with 0.9143. Okay, you make P not the subject, you calculate that it will become 164.06 kPa. Okay, and then remember, because 1 and 2 are on the same isentropic flow, they share the same stagnation conditions. Therefore, this P naught also belongs to 0.2. Okay, so now we consider this pressure ratio, P2 over PO. Okay, so we apply the P over PO ratio to 0.2 now, which is an isentropic function of the Mach number at 0.2. Okay, so right now M2 is unknown, right? Yeah, M2 is unknown. We're asked to find M2, right? Yeah, we're asked to find M2. Yeah, so we know this. We have this from here, so we can therefore fill this. So 50 divided by 164.06. Okay, so if you calculate this value out, you will get about 0.304767. Now, remember that M2 is unknown. So how do we find M2 using this? So what this says is, you go to the table and look for a pressure ratio. Okay, pressure ratio. Okay, let me, instead of writing pressure ratio, let me just write this. You look at the P over P naught column and look for an entry that is closest to 0.3047. Okay, so let's look at the pressure ratio column where the entry is closest to 0.30476. Okay, it should be here. Ah, okay, let me write that. This one. Okay, so remember, I'm asking you to find inside the pressure ratio column, right? So see, now we are focused on the pressure ratio column, and I want to look for when the entry is equals to 0.3047. Okay, close to 0.3047. And it happens to be this entry. Okay, so this is the closest that you can get. Okay, now you look at its corresponding Mach number value. 1.42. So therefore, we can conclude that the Mach number at 0.2 is about 1.42. Okay, and this is surprisingly accurate to the flow function version. Okay, so that's yeah, that's question 2. Okay, so let's answer the next part. They say sketch the shape of the channel, right? So we have found that the Mach number has a value of 1.42 at the 0.2, and the Mach number at 0.1 is 0.36. So what you need to do is identify the flow regime. So this one is subsonic, right? Because M1 is below 1, therefore it's subsonic. M2 is above 1, therefore it's supersonic. And then you look at the value of the Mach number. It went from 0.36 to 1.42, meaning it accelerated, right? It must increase its velocity so that the Mach number can increase. Therefore, we conclude that this entire flow is accelerating. Okay, it's accelerating throughout. Okay, somewhere along the flow, it must have reached Mach number equals to 1, right? Because 1 is between 0.36 and 1.42. So therefore, somewhere in the middle, it has reached Mach number equals to 1. So where the flow has a Mach number less than 1, this is subsonic acceleration, right? Because acceleration because the Mach number is increasing. Where the Mach number is greater than 1, this one is supersonic acceleration. Okay, in order to induce subsonic acceleration, you must have a converging nozzle. Okay, that the nozzle must constrict along the flow direction in order to accelerate the flow. Okay, so this one is converging. And then in order to achieve supersonic acceleration, it is counterintuitive, okay? Supersonic behavior is counterintuitive, or at least for isentropic nozzle. So instead of constricting to accelerate it, for supersonic flow, you must have a diverging nozzle in order to accelerate it. Okay, so here must be diverging. So you see, a combination of both of them will produce a converging diverging nozzle. So if you want to sketch the shape, it will be like this. So converging at first, and then diverging after that. Okay, so that's how you sketch a converging diverging nozzle. Okay, now let's move on to question 3. Okay, question 3 says that air is flowing in an adiabatic pipe with a mass flow rate of 9.07. At one section, it has this pressure, this temperature, and this area. Okay, downstream means down the flow direction. There will be another point with Mach number 1.2, sketch the flow passage, and then find the exit area. Okay, so find A2, provided that the flow is reversible. So if it's adiabatic and reversible, this satisfies the condition that it is isentropic. It is isentropic. Adiabatic means no heat transfer. Reversible means no sources of energy loss, for example, friction or shocks. Okay, so we know that this is isentropic flow. Now we sketch out this flow. So it has two main points, 1 and 2. Point 1 has conditions like so. Again, don't forget to change temperature to Kelvin. And then they tell us Mach number is 1.2 here. Okay, so how do we find what do we need to find? Okay, in order to sketch the flow passage, right, we need to know whether it's accelerating or decelerating. In order to know if it's accelerating and decelerating, we need to know the Mach number at each point. We already know the Mach number at 2. We do not know the Mach number at 1. So let's go ahead and find the Mach number at 1. The definition of Mach number is V1 over C1. Okay. C1 can be given by square root of K R T1. T1 is known. However, V1 is unknown, right? So how do we find V1? Well, we shall make use of the mass flow rate. Mass flow rate is given by rho A V, right? So now we're using the points at the conditions at 1. Do we know, okay, we know area. We do not know what it is. We know mass flow rate. We haven't yet know what is density. Find density using the equation of state. So according to the equation of state, the density is given by P1 over RT1. P1 is given, T1 is given. Okay, so that means we can find density. So change kilopascals to pascals. Okay, yeah, so this is your density. Okay, so that means now your density is known. You see, in here, V1 is your only unknown. So therefore, let's sub in the values and calculate for V1. V1 is 9.07, 178.6. Don't forget to change your area to meters squared. Then V1 is your unknown. So V1, it will be 2248.48 meters per second. Okay. Finally, we can calculate the Mach number. So take the velocity, the flow velocity, divided by the speed of sound. So K R T. You will find that it will become 3.69, which is supersonic because it's above 1. Okay. So, okay. Having found that this is m1 is equal to 3.69, we can identify what kind of flow this is. So what I mean is this. Okay, you take a look at the two endpoints. This is 3.69. but the Mach number here is 1.2. So did it increase or decrease? Here, the Mach number decreased. Therefore, you can say that this decelerates. Okay, so throughout this flow, there's a deceleration. Okay, and then also throughout this flow, right, it is supersonic, right? 3.69 is supersonic. At this end, 1.2 is also supersonic. So throughout the flow, right, even though the Mach number is decreasing, it never dipped below 1, right? It never go below 1. It is always above 1. Therefore, throughout this whole thing, it is a supersonic acceleration. Okay, it is supersonic acceleration. So how do you achieve supersonic acceleration? You need to have a diverging. Sorry, this is deceleration because the Mach number dropped. Okay, so this is deceleration. So how do you achieve supersonic deceleration? Remember that supersonic is counterintuitive. So in order to reduce the flow speed, you need to constrict the nozzle. Therefore, this must be a converging nozzle. Okay, it's counterintuitive. So according to our intuition, constricting the nozzle should increase the flow speed, right? For the same flow rate, okay? For the same volumetric flow rate. However, supersonic is counterintuitive, so constricting it will make it decelerate. Okay, yeah, so that's how you identify the shape of the nozzle. So in order to draw a converging nozzle, it just look like this. Okay, yeah. Okay, now find the exit area. So how do you find the exit area? Okay, so this is another important property that you need to know about isentropic flow. So for an isentropic flow, any two points share the same critical point. Okay, so this is a special property of isentropic flow that you need to remember. So you see, that's the special thing about isentropic flow. They share two reference states. Okay, the reference state that I'm referring to is the stagnation state and the critical state. Okay, that is a special thing about isentropic flow. Any 2 points on an isentropic flow share the same stagnation state and also share the same critical state. So the critical state is a state where m is equal to 1. Okay, so yeah, so how do we make use of this fact? How we make use of this fact to calculate the exit area, right? Okay, so you see, A1 is given to us. And both of these points, 1 and 2, let me erase this bit. Yeah, both of these points share the same critical state. So the flow of our ideas is this. They give us A1, so this is given. Okay, then we use this to find A star, the critical area, and then we use this to find A2, okay, which is what we want in the end. So okay, so that's the flow of our ideas. So take a look at the flow function table. Notice that the last column of the flow function table, so let me wait for this to load. Okay, notice that the last column of the flow function table is the area ratio, right? It is area at a point divided by the critical area. Okay, so we need to make use of this flow function. Yeah. Okay, go back here. So first, let's apply it between 1 and the critical state. Okay, apply it between 1 and critical state. We have A1 over A star, right? And this is a function of the Mach number at point 1. Okay, and we've already found that Mach number at point 1 is 3.69, right? We already found it here. Sub in the known values. So A1 is given. A star is unknown. And this, right? So this, we find it from the tables. So what this says is, you go to the table, look for the row where Mach number is equal to 3.69. So here, okay, this is the row where Mach number is equal to 3.69. The last column is the area ratio, and it says 8.0944. So let's take that value, 8.0944. You calculate A star. A star will be equal to 6.376 meter squared. Wait, is it meter squared or cm squared? Cm squared, right? Yeah, it's supposed to be cm squared, sorry. So it's cm squared. Okay, now, okay, let's go back here. We've already completed this half of the process. Now we are entering the second half of the process. So how to relate A2 to A star? So take again the area ratio, except now you apply it to 0.2. So again, this is a function of your Mach number at 0.2. Do we know the Mach number at 0.2? We do, right? I believe it's 1.2. Yeah. Okay, so this is 1.2. Okay, so sub in everything you know. We do not know what's A2, but we know what's A star, right? It's 6.376. Then this you obtain it from the table, and then you need to look for when the Mach number is 1.2. So go find when the Mach number is 1.2. So this is the row where Mach number is 1.2, and then the area ratio is 1.0304. Yeah. Okay, so we use that value. And A2 is equals to 6.57 cm squared. Okay, so this is how you get the area. Okay, now we move on to question 4. How long have I been recording? Been recording for 40 minutes. Okay, so air is flowing through a converging nozzle and discharging into the atmosphere. At one section, we have these conditions. The flow is just choke. Find the pressure and Mach number at this location. What is the choke area? Okay, so let's sketch the problem out first. Okay, okay, that's about as much information to give. So, what are we expected to find? We are expected to find pressure at 0.1, Mach number at 0.1, the area of the throat, and the mass flow rate. Okay, so what to do? They told us that the nozzle is discharging to the atmosphere, and this is the important clue that the flow is just choked. If you know that the flow is just choked, right, that means you can infer, okay, what you can tell is that the exit pressure must be equal to the back pressure, which is equal to 101 kPa. Okay, I explained this thoroughly in the previous video. Okay, it's quite a long explanation, so I'm not going to explain it here again. So what I recommend you to do is watch that video to explain why is this the case. Okay, so go ahead and watch the previous video. I'll probably put a card in the right hand corner. Yeah, so you can go find the explanation of why this is the case. Okay, so now for now, just believe me when I say that when the flow is just choked, the exit pressure will be equal to the back pressure. Okay. So yeah, now we can go ahead and find things. So again, in compressible flows, you always want to find the Mach number first. So we can easily find the Mach number at 0.1. Mach number is given by velocity divided by speed of sound. Then this is given. This can be found using square root of KRT 1 So this is 200 divided by square root of k r T1 is what? 37613. Okay, so your Mach number is 0.600, which is subsonic. Okay, then this will help us find the pressure at point 1. Okay, so we already found M1. Now this will help us find the pressure at point 1. Why? Because this flow is isentropic. Isentropic means that they share the same stagnation conditions. So the exit point and point 1 share the same stagnation conditions. So therefore, we shall find P naught first. So in other words, okay, my idea is this. PE will help me find P naught, and P naught will help me find P1. Okay, so that's the flow of my ideas. So let us apply the pressure ratio to the exit point first. So PE divided by P naught. Okay, this pressure ratio is a function of the Mach number at the exit. Now, what is the Mach number at the exit? Because they say this is choke, right? Choke means that the choke must necessarily be m equals to 1. Okay, me equals to 1. Okay, choke means the choke is a critical state. So this is 1. Okay, so now you go to the flow table. Sorry, let me just fill in whatever you know first. So we already know that the exit pressure is this. Is unknown. Now, find this from the table where Mach number is 1. So you go to the table and you look for when Mach number is equals to 1. Okay, so Mach number equals to 1 is over here. Right, and we are looking for the pressure ratio, which is this one. Yeah, okay, 0.5283. So if you calculate the stagnation pressure, it will be 191.179 kPa. Okay, so we already finished this half of the process. Now we want to complete the second half of the process. So now apply the pressure ratio to 0.1. So P1 over P naught is a function of M1. Right? Yeah. And do we know M1? Yes, we already found M1 here, right? Here. So you sub 0.6. 0.600 in. P1 is unknown. P0 is what we found here. 191.179. Then this, you obtain it from the table where the Mach number is 0.60. Okay, so go back to the table. Then we shall find the Mach number equals 0.60. Okay, so Mach number equals 0.60 is over here. Okay, and we're looking for pressure ratio, so this one. Right? Yeah. So replace this value with 0.7840. And the pressure ratio will be 149. Sorry, the pressure is this. Right? And this is correct because I remember the lecture solution was 150 kPa. Okay. So we already found the pressure, we already found the Mach number. Now we want to find the throat area. Okay. So how to find the throat area? The throat area is found using the critical state. Okay. Because area, right? You cannot use stagnation conditions. You must use a critical state. Okay? That's a fact. That's a fact. So they give us area at point 1. So therefore, we need to apply the area ratio at point 1. Okay. So A1 divided by A star. Okay. This is a function of the Mach number at point 1, which we already found just now is 0.600. Right? So they told us that this area is 0.05. And A star, right, means the critical area. And where is the critical area? The critical area is the cross-section area where Mach number equals to 1, right? Mach number equals to 1. Therefore, this point is the critical point, and for an isentropic flow, the critical point occurs at the throat of the nozzle, okay, the throat of the nozzle. Therefore, A star, right, can be directly replaced with AT. Okay, so A star is directly replaced with AT. Then how do I get this? I go to the table and look for Mach number equals to 0.6. Should be here, I think. Yeah. So I'm looking for area. So this one, 1.1882. Okay, you meet the throat area, the subject, you should get this. Okay, finally, we need to calculate the mass flow rate. Okay, the mass flow rate, well, let's just use the conditions at point 1. Okay, we don't have density, but density can be found using equation of state. Okay, in other words, the ideal gas law. The pressure we got just now was here, right? Except we need to change it to Pascal. So multiply by 1000. And then the temperature is given. Okay, so this is our density. This is known. This is known. V1 is also given. Yeah, V1 is given to be 200. So therefore, we can find mass flow rate. 9 times 0.05 times 200. Then in the end, we get 18.9 kilograms per second. Okay, so this is how you do. Oh, wait. We still have one more question, right? Yeah, there's still one more question, which is question 5. Okay, but question 5, let me just show you. Yeah, question 5 is normal shocks. Okay, so up until question 4, we have also only be using the isentropic flow table. Now let's take a look at how we use the normal shock table. So we have a constant area duct. Inside there's a shock. The upstream and downstream of the shock is points 1 and 2. Then before the shock, we have these stagnation conditions. Point 1 has a Mach number 2.5. So we want to find P2. So find P2. Okay, so how do you find P2 using the tables? Okay, first thing first is, in order to find P2, we must necessarily find P1. So let's go ahead and find P1 first. So if you look at this one, we use the isentropic flow table. Why? Because joining this point to this point, so point 0, 1 to 1, this is the isentropic flow. Okay, we assume to be an isentropic flow. Okay, actually, because this is the isentropic stagnation state, yes, it's necessarily an isentropic flow that connects 0, 1 to 1. Okay, yeah, so it's necessarily an isentropic flow that connects 0, 1 to 1, because this is a isentropic stagnation state. So let's go ahead and apply the isentropic flow table to find T1. Okay, so this pressure ratio is a function of the Mach number at point 1, which is 2.5. So you substitute whatever you know. So P1 is unknown. P01 is 650. Yeah, this one, you go to the table, look for Mach number at 2.5. Okay, so Mach number at 2.5 is somewhere down here, I think. We're looking for pressure ratio, right? So this is that 0.585, yeah. So from the table, this will be Okay, so you make P1 the subject. Should get about 32.5. Okay. Having found P1, you can now find P2, right? How? Okay. You see, what kind of process joins joins point 1 to point 2? Is it an isentropic flow? No, right? It is a shock. This is a normal shock. Okay, so therefore, in order to relate the properties between 1 and 2, we need to go to the shock table, not the isentropic flow table. Make sure when you use the tables, right, you use the correct tables. So let's go to the shock tables. So here is a normal shock table. We want to find when the Mach number at point 1 is 2.5, right? Okay, before that, let me write down what we need to do. So, okay, never mind. We go to the isentropic, the shock table, and then look at the headings here. What point is relevant? Which column is relevant to us? Okay, the column that is relevant to us is the pressure ratio because we want to find P2, right? So therefore, this column is relevant to us. Okay, so we write P2 over P1 is a function of the Mach number. Okay, the function of it is a function of M1. Okay, so let's write that down. Okay, so what we write here is P2 divided by P1 is a function of the Mach number at point 1, which is 2.5. So you see, this time I'm not gonna write Isen here. Instead, I'm gonna write shock because this time we use the shock table, not the isentropic flow table. Okay, so let's fill our knowns. Our knowns is this is known, right? And then this one we find on the tables. So according to tables, you go look at the Mach number when it is 2.5. So 2.5 will be here. Then we're looking for the pressure column, right? Which is, yeah, down here. So 7.1250, this one. So you'll find that P2 is equal to 270.928 kilopascals. Okay, now the second question. The second question says, find the pressure reached by decelerating the flow isentropically to the same subsonic Mach number. So that means we need to find M2 first, okay, in order to be able to have enough information for this question. Let's find M2. How do we find M2? Okay, it's very simple. M2, right, is simply a function of M1, and M1 we know is 2.5. Okay, has a value of 2.5. And this you go to the shock table because remember 1 and 2 are related by a shock. So go to the shock table, go to M1 is equal to 2.5. Okay, so we are already at this highlighted here. The column which gives M2 is the second column here. Okay, so M2 has a value of 0.5130. So therefore, M2 is 0.5130. Okay. So what this is telling us is the new problem is like this. So we have the stagnation conditions, right? The stagnation conditions are the same as before. So T naught is equal to 550. P naught is equal to 650. And then point 2 has a Mach number of 0.5130. The question is, what is the pressure here? So this is all related by a isentropic flow. Therefore, we use the isentropic flow table. So P2 divided by P naught is a function of the Mach number at point 2, where the Mach number is 0.513. Okay, so let's fill up our knowns. P2 is unknown, P naught is known. This one is found at the table where M2 is equal to 0.51. But the thing is, since the Mach number is served to 2 decimal place, just round it off to 0.51. Okay, so go to the isentropic flow table, and you find Mach number is equal to 0.51. So it should be down here. Yeah, here. Then we're looking for pressure ratio, right? Pressure ratio should be this column, I think. Yeah. Okay. 0.8374. Then when you calculate P2, you will end up with 544.131 kPa. Okay, so that's basically how you do tutorial 2 using the tables. Okay. In the previous videos, I showed you how to use it, how to do it using the flow function formulas. But in this one, I showed you how to use the tables. Okay, yeah. So if you found these videos to be helpful, please donate to me on PayPal. Yeah, thank you.